In our 44th class of this dairy and food process and products technology, we were discussing about the milk processing. Right, in earlier classes we were discussing about milk processing, and we came up to milk pasteurization. Of course, pasteurization is one such a process in milk, liquid milk, not only in liquid milk, in many liquid foods, that serves the major purpose. We said the reasoning, but will again come in detail a little more. Right, let us first, okay. So, we were in the UHT, right. So, some disadvantages associated with high temperature are like this, that there is a possibility of alteration of milk proteins, and this can affect the properties of such milk when used to make other food products. And in that, the major one which comes in is the Maillard reaction. And you remember that we had said in earlier classes that as and when the new things will come, we will try to defend them or explain them as much as possible, because that becomes generalized not only in liquid milk or liquid food, but also in solid foods, right. So, if we look at that, this elevated temperature causes the Maillard reaction, and then it comes, what is that? What is the Maillard reactions? In that, if you remember, we had said there are two types of or three types, in general two types, and one is enzymatic and another is non-enzymatic, right. So, that browning, we divide them into two types. This is true for all foods, whether solid or liquid does not matter, it is associated with all foods. So, these two types of browning reactions, that could be in fruits and vegetables, that could be in milk, that could be in any solid or liquid food material, right. So, enzymatic and non-enzymatic, these two types of browning, they are associated with this, that this let the whole thing come in front of you. Yeah. So, here we have written fruits and vegetables, and here I write and liquid foods, right. So, fruits and vegetables, liquid foods, and this is under solid food, right, and that is under liquid food. So, under for them the browning reaction takes place in enzymatic manner or in non-enzymatic manner. So, if it is enzymatic manner, then this is controlled by the enzymes, right. We gave the example earlier that if we are making, say if you are cutting apple if you are cutting, or if you are cutting potato, very handy example, because every now and then you come across potato, you come across every day. Apple may or may not be you are coming across every day, but so if you cut it, even those I said that if when people are making prasads, right, or offering to the gods, then those prasads, they also become black, brown, different colors depending on what are the fruits you are supplying. Banana, one such, it becomes black. then apple, potato, these things we come across very often. So that comes under the browning. And the other one, which if you remember, I gave the example of mummy and seniors, grandmummy or others, they are preparing for you, for God or whatever, payasam, things like that, or kheer. That time boiling milk for a longer period, and when started it was white milk, but after long time it became brown, though nothing has been given. Nothing to that milk had been given, not even the sweetening, not even any other. So that happens under non-enzymatic browning, right? And in non-enzymatic browning, there are again two types. One is called caramelization and another is called Maillard reaction. So this caramelization and Maillard reaction, that is associated with the food materials, and everywhere that Q10, if you remember, we had said this Q10, that is always associated, right? So Q10 means the more the temperature, the higher is the rate of reactions. So this is true for every food material. The higher the temperature, the higher the rates of reactions, that is any type. So when kheer or payasam was being prepared, that was at high temperature, so that rates of reactions, that is Maillard reaction, that was high, caramelization, that was high, that is why the browning took place. So non-enzymatic, again we divide them into two. One is caramelization. I don't know why the color of the pen is so caramelization, right? And another one is Maillard. I'm sorry that the writing with the pen. Hopefully it is understandable, right? So these two we divide them into one with caramelization and another is with the Maillard. This non-enzymatic, so what happens? With enzymatic, it goes there, not non-enzymatic. It should have been, the arrow should have been up to that, right? So let us take this arrow up to that. So it is non-enzymatic, no enzymatic. So if it is enzymatic browning, oxidation of phenolic compounds, that happens, right? So for which the sensory properties like color, flavor, they got changed. So out of which many could be bad, some could be good. When you made that or kheer, that color was desirable, right? So because that was different from the milk, so that was desirable. So and it also produced some flavor, not only color but also some flavor produced. So this flavor and color was welcomed in that process, but in many processes they are not, right? So depending on what you intend, what is your end use, some could be good, some could be bad, right? So bad and good depends on your application, your use, right? So if we look at then the enzymatic browning, if you look at the enzymatic browning, then we look that this enzymatic browning is done by polyphenol oxidase, right. So, let the entire thing come in one before you, and I think some more will come. This. So, poly-PPO, or that is called polyphenol oxidase. There are many enzymes which are associated with enzymatic browning. One such is polyphenol oxidase, right. We cannot give all the examples because time is the primary thing, right. We have to finish up the course within the stipulated time. So, we cannot give all the examples, but polyphenol oxidase is one enzyme which commonly used, as you see, apples, avocados, lettuce, potatoes, etc., right. So, there it is applicable. So, many other enzymes are also there which are associated with this, right, and in many. So, those are for browning of that particular food product, right. So, what happens in that enzymatic browning? I could not show you because of the time constraint that this enzymatic browning that happens, this oxidation under a free radical mechanism, that is one, right. Free radical mechanism, that you have RR, if you have, then that comes a free radical R plus R maybe, right. So, this free radical, when it is generated, that free radical comes under reaction and produces different end products. One here we are giving example that the reaction which is associated is, say, 4-methyl catechol. This is the one of the substrate. So, in presence of oxygen and the enzyme, and there could be some catalyst like, say, copper or something, which also may act as the catalyst. So, that reacts with oxygen, forming an intermediate compound called quinones, right. This is the structure of the quinones. This is orthoquinone, that can be paraquinone if there, right, or if this is also with a double one here, then that could be orthopara. This is ortho, meta and para. This is paraquinone. This is right. So, there in all the cases, these quinone derivatives, they are formed, and with one molecule of water, it makes an oxygen, right. Okay. If it is, this is one, so it is a generalized equation that leads to this melanins, or if it is not this part, amines and oxygen that could form, or maybe non-enzymatic condensation that may happen and may produce melanins. This is okay with respect to the enzymes, right. With respect to enzymes which may produce soluble or insoluble brown polymers, they are called melanins or melanoidins, right. Let us clear, melanins or melanoidins. Right. So, these melanoidins, I think with the pen, some pressure or something, some press, these things are required, that is why this may be so like this one is light, this one is dark, so you have to press. Okay. Then this happens soluble and insoluble brown material, that those are melanoids or melanoidins, right. So, if we look at the other one, this is the enzymatic one, and there I said in many cases this mechanism follows your free radical mechanism, right. At the other one, that Maillard reaction which takes place, Maillard reaction is non-enzymatic, right. So, this happens with caramel or caramelization. Caramelization is basically when you are heating sugar. When you are heating sugar, that times caramelization is taking place. That crust on the bread, there it is caramelized, right. That brown color on the bread, that is caramelization. So, similar to that, many are there. You have seen that mummy and grandmummies are putting some sugar in your daily food preparation. That is not for making it sweet, but a kind of caramelization happens, and that improves the flavor as well as the color. So, that is why that is given, because not sufficient quantity of sugar is given so that it becomes sweet, not for sweetening, but for introducing some flavor or inducting some flavor as well some color through caramelization. But the reaction is very complex, and that also at the end produces melanoidins or melanoids, right. So, if we look at this Maillard reaction, then we see that this is a Maillard reaction I had written in vertical form, right. So, Maillard reaction, that is this is a general scheme. This was developed in 50s, early 50s, right. So, this is the one source it has been taken, that aldose, right. This is aldose, means aldehyde which are in the sugar form, right, and amino group, right. So, when they are reacting, eliminating water and producing N-substituted glycosylamine, right. This is one of the beginning of the reaction. Then you see going lot many paths. It is undergoing paths. This path coming to some intermediate likes, right. 1 amino, 1 deoxy, 2 ketose, or it may be producing like fission products, that could be acetal or butane dione or 2-oxypropanol, etc., right. That may also come from here, right. This may lead to Schiff base of HMF or furfural, right. Or there it may go to HMF or furfural, some sugars may also add here, or from here it may leave water. So, it was leaving water, and a reduction reaction may take place, right, which may produce dehydro reductions that could be dehydro reductones, not reductions, reductones that could be again another intermediate, or from here again some more intermediate could be, depending on different path, like Strecker degradation, right? So that produces aldehydes, right? There are many intermediate paths, like Strecker degradation is one, and a ketoenol mechanism, that could be another. So many such reactions do happen. So intermediate aldehydes or aldols and N-free, that is nitrogen free polymers, that also could be, or ultimately it comes to melanoidins or brown nitrogenous polymers and copolymers that may form here, right. So you see in so many parts it is coming. This is also very not so complicated structure. There are many cases, in many books also it is available, that this scheme is even more complicated, and they had introduced intermediate pathways, intermediate processes, intermediate products which are developed. Now it depends on the extent of the reaction where it is getting ended. That is why it is very difficult in Maillard reaction to predict what will be the end product, right. What will be the end product? It can stop here, it can stop here, it can stop here, it can stop here, or some or all of them might have been produced. So some of them or all of them might have been. So that is the beauty of this reaction, this Maillard reaction and caramelization that may happen, right. So preconditioning and participating compounds and the complexity are like this. Glucose glycine, more than 24 products could be found. Xylose glycine, more than 50 products also could be found, like that. So depending on how far you are extending, how far your reaction is happening, how long it is happening, all these will dictate what could be the end product, right. So it is very difficult to pinpoint that through that Maillard reaction you got this as the end product. That is why you will always see that in general these food scientists and technologists, they do say that sugar-amine reaction produces melanoidins or melanoids or melanins, whatever be the naming, right. They are all synonym, and it follows different pathways, right. It follows different pathways, and in caramelization also you will have the same. You will have the same in caramelization, right. Now let us look into some other aspects also, that when we are applying high temperature pasteurization, then you can heat milk to 60 degrees centigrade for not less than 30 minutes. That is called low temperature long time pasteurization, and alternatively you can heat up to 70 degrees centigrade for not less than 16 seconds, right. That is high temperature short time or HTST pasteurization or equivalent. So, these time temperature combinations have become proven to be sufficient for the destruction of the pathogens and the enzyme phosphatase. We have said that this phosphatase enzyme is one of the most heat resistant, enzyme, so that can be destroyed by this. A negative test results for the alkaline phosphatase test confirms the efficacy of the pasteurization. Right. So, let us proceed now quick because our total time is fixed. Frozen dairy dessert makes pasteurization. When we are doing dairy dessert, will come subsequently in other class, that when you are making ice cream, that is a dairy dessert. So, that time you have to pasteurize a lot of ingredients to get the ice cream mix. So, there of course, this pasteurization will, the time temperature combination will be different, right. So, very many frozen dairy products exist in the market. When pasteurization of ice cream or ice cream milk heat the product to at least 69 degrees centigrade for not less than 30 degrees centigrade or 80 degrees centigrade for not less than 25 seconds. Any other time temperature combination must be approved, for example, 83 degrees centigrade for 16 seconds, etc. But that combination time temperature you have to generate, right. You have to generate and see at the end through any enzyme which is highly heat resistant, that if that inactivation is over, then you can conclude that your this thing is over, pasteurization is over. Okay. Pasteurization of enriched milk products like milk based products with 10% butter fat or higher or added sugar, for example, cream, chocolate milk, etc., should be heated to 6 degrees centigrade for 30 minutes or 75 degrees centigrade for effective pasteurization. Now, let us quickly go through this. The objective of pasteurization we have already said many times, so I will just read it out. The chief objective of milk pasteurization is to destroy pathogenic bacteria that could have a public health concern. By destroying these microorganisms, the product becomes safe and for public consumption. Secondly, pasteurization eliminates destructive bacteria and enzymes that could cause spoilage of the product. This leads to a prolonged shelf life of the milk. Pasteurized milk is commercially sterile, which means that they are not entirely rid of bacteria. That means you are not totally making bacteria free. One should compound their preservation with another method, usually refrigeration. In modern milk processing plants, the plate heat exchanger is connected to a separator and a homogenizer in the same line. The milk separators help in butter fat standardization, while the homogenizer breaks down fat globules into tiny microbes that remain suspended throughout the milk. It prevents formation of cream layer when the milk is left and standing for a long. This we have said many times, so that is why I just went through rapidly. Some steps which we have to go through during pasteurization, but hopefully now the time is over for this class. We will carry over to the next class. Okay, thank you.